Hello, Math A Honors students. This is Mrs. Stengel. I hope you're having a wonderful day. Thank you so much for joining me on our 7.1D lesson. We're going to be covering problem solving with area. So hopefully by now you've been able to navigate Google Classroom, and under the classwork stream you found the assignment 7.1D. You can either print it as I've done and hand write the answers and the work right on the paper, or you can use your computer and edit it with a PDF editor. Or you can use a lined piece of paper and write right on that as well. You don't need to copy down all the word problems, just show your work underneath each problem with labels. All right, so let's begin. The goal of this lesson is we want to use our knowledge of perimeter and area to solve real world problems. So in problem number 1, it says Kara and Charisse are in a quilting competition. Both are stitching rectangular shaped quilts. So far, Kara's has an area of 2,278 square inches with a length of 44 inches. And Charisse's quilt has an area of 2,276 square inches with a length of 47 inches. Whose quilt is wider? By approximately how many inches is it wide, and round to the nearest hundredths. So it's helpful if you draw a diagram to fill in some missing measurements and to fill in measurements that are given. For instance, for Kara's rectangular quilt, she has an area of 2,278 with a given length of 44 inches. And what's missing is her width value. And for Charisse, we can do the same thing. We can draw a diagram to show what is given and what is missing in our rectangular quilt. Her area was 2,276 with a length of 47, and we have an unknown value for our width. So I would use the formula for a rectangular for area, which is length times width, to solve for my missing width for each one of these rectangles. So I'm going to plug in the area for Kara's rectangular quilt and her length, and I'm going to solve for width by isolating my variable and dividing both sides of my equation by 44. So that's going to give me a value of 51.77 inches for Kara's width. So for Charisse's width, I'm going to use the same formula, but I'm going to plug in her values for her area and her length. And I'm going to solve for width by isolating the variable, divide both sides of my equation by 47. And I get that her width is 48.42 inches. So we're going to answer the question, whose quilt is wider? So Kara's quilt is wider. I'm going to use a complete sentence. So Kara's quilt is wider. And I want to know by how many inches it is wider. So I'm going to subtract Kara's width, 51.77 minus 48.42 to find the difference of these two widths. That's going to give us 334. So Kara's quilt is wider by 3.34 inches. All right, moving on to number 2. It says Rufina bought 2 12-foot pieces of lumber and 2 8-foot pieces of lumber to create a border for her garden in her yard. She wants to use all the wood to enclose the garden. How should she use the 4 pieces to create a rectangular garden of largest possible area? What is the largest area she can get with her 4 pieces of wood? So when we talk about area, we want to maximize the square inches that we can fit inside of this border. So looking at the border, which is the perimeter of this shape, I have 2 12-foot pieces and I have 2 8-foot pieces. So the border of my shape is 40 feet. I want to use that information to make and maximize a shape that will help me get the largest possible area. So one way that we could do this is we could just use the dimensions that are given. We could use 12 times 8, which is 96 feet squared. So 96 may not be the maximized area for this particular garden. So we can look at some other ways to maximize the area by looking at perimeters of other shapes that would also equal 40. Depending on whether or not you can cut the wood, let's assume that you can cut the wood. And if that is the case, then I can reshape the wood into pieces that are 10 foot long and 4 of them making my perimeter also equal to 40 feet. So if I were to find the area of this square, I would multiply 10 times 10, which would be 100 feet squared. So for me to maximize the area, I would want to create a square shape. So to maximize the area, create a square. All right, let's move on to number 3. A triangle has an area of 90 square centimeters. If its height is 15 centimeters, what is the length of the base? So I'm going to use the formula for the triangle's area, which is 1/2 base times height. And I'm going to plug in the information that they give me. They give me that the area is 90. We don't know the base, so we're going to leave that as a variable, but that we are given the height is 15. So I'm going to solve this equation for the base. One way you can solve it is you can multiply both sides of this equation by 2. So you can cancel out the 1/2. So 90 times 2 is 180. Now I'm going to solve for b by isolating that variable. I'm going to divide both sides of my equation by 15, and I'm going to get that b is equal to 12 centimeters. Sketch a triangle with an area of 90 square centimeters, height of 15, and base you found in part A. Is there more than one triangle you can draw with those dimensions? So if I was using the same base of 12 centimeters and the same height of 15, one way that I can draw this triangle is by creating a 90-degree angle. Another way I can draw this triangle, as long as I don't go above my apex and I don't go higher than 15 for my height, I can still have a base of 12, but I can extend my angle out even longer and wider, and I can create a triangle that is much wider of an angle. So in doing this, you can actually draw an infinite amount of triangles. So the answer to the question is you can draw an infinite amount of triangles. Okay. In letter C, it says a new triangle that has an area that is 150% of the original 90 centimeters squared triangle. State one possible set of dimensions for the new triangle. So if we are to increase our original 90 centimeters by 150%, then I need a new area of 135. So this is my new area. Now I'm going to use that 135 and I'm going to state some possible set of dimensions for the new triangle. So if 135 is my new area, and I'm still using the same formula, 1/2 base times height, I'm going to multiply both sides of my formula by 2 to cancel out my fraction. So I have 270 is equal to base times height. So I challenge you to pause the video and come up with numbers that could work for the base and the height. Hopefully you came up with the easiest one. So the easiest one that I was thinking of, for example, would be the base is equal to 270 and the height is equal to 1. Hopefully you guys came up with some better bases and heights. Maybe you came up with 9 and 30. Or you came up with an easier one like 27 and 10. Either way, as long as you can get the base and height to multiply together to give you 270, those are some possible set of dimensions for your new triangle. Okay, let's go on to our next page. So on the next page, it says that Julius drew a triangle or trapezoid, that had bases of 15 and 11 inches and a height of 4 inches. What is the area of the trapezoid Julius drew? So I'm going to use the information that's given. I'm going to draw a trapezoid that has bases of 15 and 11. So I'm going to put my longer base on the bottom, and I'm going to put my shorter base up at the top. And it says that we have a height of 4 inches. So I'm going to label that as well. Remember, the height runs perpendicular to the parallel bases. So what is the area of this trapezoid? We're going to use the formula 1/2 base 1 plus base 2, and we're going to multiply that by the height. So I'm going to plug in my bases, which is 11 and 15, and then I'm going to multiply that by the height. That's how I'm going to get the area of this figure. So you can do parentheses first using our order of operations. So I would add 11 and 15 first. That's 26. Okay, I'm going to take 1/2 of 26, and then I'm going to multiply that by 4. So for my area, 1/2 of 26, I'm going to do that first. That's 13 because I like to multiply those two first. And then 13 times 4 is going to be equal to 52 inches squared. Okay, the next question says, can you draw a trapezoid that has the same height of 4, but different bases with the same area? Okay, so I want to have my base 1 and my base 2 equal to 26 from the previous problem. And so I'm going to come up with numbers that add up to 26. So I challenge you to pause the video and think of some numbers that would add up to 26. Okay, so hopefully you came up with the easiest one possible. One of those options could be 1 plus 25 is equal to 26. I'm using whole numbers in this case. So really, there could be a lot of different varied answers to this as long as you can get your two bases equal to 26. You could have used 14 and 12. I'll draw a picture for you guys because it does say, can you draw a trapezoid? You could have used 25 and 1, which would be a little bit longer. It'd be a really, really short one up there like that. Same height though, same height of 4. So there's a lot of different versions that you can do for that problem. Okay, for letter C, it says draw a trapezoid with the same height, but with bases that are 5/2 scale factor of the original trapezoid. So let's go back to the original trapezoid. It had a base of 11 and a base of 15 with the height of 4. Make sure I have my right angles in here. Okay, so I have the same trapezoid, but this time I need to make my bases be 5/2 of the original. So this is 27.5 inches. This one is 37.5 inches. So those are my new bases. Now it says, what is the area of the new trapezoid? So I'm going to use these new bases and my formula for the area of a trapezoid, which is 1/2 base 1, which is 27.5, plus base 2, 37.5. And I have the original height of 4. That hasn't changed. So this is 1/2. You know what? Actually, I think I would like to cancel the 1/2 and the 4. That's actually probably the easiest step right there. So 1/2 times 4 is 2. I can also add together the 27.5 and the 37.5. That's 65. So I'm just going to multiply 2 times 65. A little out of order, but that's okay. So this area is going to be equal to 130 inches squared. All right, so you can use order of operations and do parentheses. You can multiply here as long as you are following your order of operations and you're still getting your new area to be 130 inches squared. Okay, so for number 5, the diameter of the Earth is about 7,926 miles. Find the distance around the Earth at the equator. Okay, so the equator is the largest horizontal line that's around the Earth. So we have our picture here. We have an equator that is 7,926 miles. So since it's the largest horizontal circle around the Earth, that can be considered our diameter. So we're going to be looking at the circumference because that's what distance around something is for our formula. So we have pi times diameter for the circumference, and we're going to multiply pi times 7,926. So this is going to be an approximation. So I'm going to use the approximation symbol and say that the circumference is approximately about 24,887.64 miles. And then it says, if there are 5,280 feet in every mile, what is the distance around the Earth in feet? So I'm going to take my approximate answer from letter A, and I'm going to multiply that by the fact that there are 5,280 feet in every mile. So this is going to be an approximate answer, and I'm going to get 131,406,739.2 feet. Wow, that's a big number. Okay, and our last page, we're going to move on to problem number 6. So it says in problem number 6, a circular swimming pool with a diameter of 32 feet is located exactly in the middle of a 40 by 40 foot square. So we're given a diameter and we're given a 40 by foot square lot. For safety reasons, the lot needs to have an 8-foot fence on the perimeter of the entire lot. How long will the fence need to be? So let's draw a diagram to help us solve this problem. We have a 40 by 40 foot square lot, and we have a swimming pool that is located exactly in the middle of our lot, and the swimming pool has a diameter of 32 feet. How long will the fence need to be? So we're using the outside border, so we need to find the perimeter of this square, which is actually pretty easy. We're going to do 40 times 4 because squares have equal sides, and that's 160 feet. If the fence was around only the circular pool, how long would the fence be? So because we're talking about a circular pool, we need to use the circumference formula, which is pi times diameter. So I'm going to multiply pi times 32, and that's going to be an approximate answer. It's about 100.48 feet. So the next question says, explain how much longer a fence around the whole yard is than a fence only around the pool using percent of increase. So first of all, let's go back and recall the percent of increase formula. Percent is always out of 100. So we need to make sure that if we are doing a percent of increase, that we add it to 100. It's always out of 100. And we are going to compare it to the new and the original amounts. So I'm going to use this formula and the fact that our perimeter is 160 feet for the distance around the border lot versus the circular pool. And I'm going to plug in our formula. And since we don't know the percent of increase, I'm just going to leave it as x over 100. So the new perimeter is 160. The original is 100.48. So I think it would be easier if we simplified the right side of our equation and did 160 divided by 100.48. So that is about 1.5924. So I'm going to use that information. I'm going to cross multiply the 100 and the 1.5924. So I'm just going to move the decimal place over 2 places and make it 159.24. And then to solve for our percent of increase, I'm going to subtract 100 from both sides of my equation. And I'm going to get x is 59.24. So we have a 59.24% of increase. All right, and now for our last problem. It says for number 7, a rectangular garden is 75 feet by 65 feet. One semicircle pond with a diameter of 8 feet is in the garden. Okay, let me underline some important information here. One triangular pen with a base of 10 feet and a height of 5 feet is also in the garden. The rest of the garden is covered with grass. How many square feet to the nearest tenth are covered with grass? We're going to use 3.14 again for our approximation for pi. So let's draw a diagram. We have a rectangular garden that is 65 by 75 feet. One semicircle pond, anywhere inside here, has a diameter of 8 feet. which means that we have a radius of 4, and one triangular pen with a base of 10 feet and a height of 5. Anywhere you want to put inside that figure. Okay, the rest of the garden is covered with grass. So let's go ahead and solve for the area of the grass. We need to find the area of the larger rectangle and subtract it from the area of the triangle and the area of the semicircle. So for the area of the rectangle, we're going to multiply 65 times 75. For the area of the triangle, we're going to do 1/2 base times height. And for the area of the semicircle, we need to find 1/2 of pi times 4 squared. Okay, so let's simplify this a little bit further. 65 times 75 is 4,875. 50 divided by 2 is 25. And last but not least, we have 1/2 of 16, which is 8 pi. I'm going to simplify this a little bit further. We have 4,875 minus 25. 8 pi is 25.12 as an approximation if you're using 3.14. So subtracting all these from left to right, our final answer for the area of the grass is 4,824.9 feet if you're rounding. I got 4,824.88 feet, but it says up here that we need to round to the nearest tenth. So if you look at the 8, it's in the tens place value. I'm going to round that up to 9 for my final answer. So I hope you had a wonderful time following along with my lesson. Thank you so much for stopping by. I will see you next week. Bye, Math A Honors students.